So last time we started this section 15.7 and we looked at this theorem called the second partials test. It's the second partials test because you need to go find the second partials to perform the test. It's also known as the D test. D stands for determinant, because when you do the fxx times ffy minus fxy squared, you're actually finding the determinant of a matrix that contains the second partials. Okay, so the idea is first you got to get the critical points before you can even do the D test. So how do you get that? You find your first partials and you simultaneously set them equal to 0. And this is the hardest part because this is where you have to solve either linear or nonlinear systems of equations. And this is the algebra part that gets a lot of students in a lot of trouble, and then they get these wrong critical points. And I don't even grade the rest of your problem if you get totally incorrect critical points. Like, what's the point? Well, I got something and at least I applied the D test. Yeah, but that's very formulaic. So the hard part is going to be, can you do the algebra right there? That's going to be the sticking point. After you get your critical points, you form the D quantity, which is this guy right here, fxx fyy minus fxy squared, and then you plug in your critical point, or points, yeah, individually, of course, like more than one critical point is possible. And then there are 4 possibilities that could happen when you examine your D value. If your D ends up being a positive value, one of 2 things can happen. So if your fxx evaluated at your critical point is also positive, you have a relative minimum. On the other hand, if D is positive and fxx is negative, you have a relative max. Please don't get these reversed. It's very common for most humans. We always think, hey, if both things are positive, that means we're maxed out, right? No, you have a minimum. And so let me remind you of why that's kind of the case. If you recall from Calc 1, let's do a Calc 1 review again. The second derivative test said the following. If you have a critical point, say x equals a is a critical point, and you go get your second derivative and you evaluate your second derivative at that critical point. If you got a positive number, what that meant is that your graph had a concavity that was concave up, which means you have a rel min. On the other hand, if your f double prime evaluated at your critical point was a negative number, so do you see what I mean? When this is positive, you've got a min. When your f double prime was negative, that would mean that you're concave down, and then you would have a rel max. So just like in Calc 2, when you performed the second derivative test in order to distinguish whether you had a max or a min or none of the above, you had that sort of backwards thinking, is that if your f double prime is positive, it's concave up, so you have a min. If your f double prime is negative, it's concave down, so you have a max. The same kind of backwards thinking. So if you can kind of think about that, if that helps you from your Calc 1 days, from the second derivative test, that's the analog, if you will. Okay, and then the last 2 possibilities for this D test are, what if your D is a negative value? You don't even have to bother looking at fxx. You're done. It's a saddle point. We talked about what a saddle point was last time. Now, if your D is equal to 0, and this can happen, that means your test is inconclusive. That doesn't mean that there are no extrema or anything. There could be tons of extrema. It just means that this D test it fails. So it's not always working for you. So at that point, you may have to maybe go start plugging in values, or maybe even look at a table of values and try to figure out. Computers can help also. Okay, so here is example 3. In example 3, we have a function here of 2 variables. Okay, and I'm gonna put you guys in breakout rooms and have you try this on your own. So let me just walk through the procedure. Step 1 is you're going to find fx and set it equal to 0, and you're going to find fy equal to 0, and then you're going to solve the system to find the critical points. or you may only have 1 point. So there may be 1 or maybe 2 or maybe 3, 4, 5, 6, 7, who knows? So after you get your critical point, then you're going to do step 2. You're going to form D. Well, D is this quantity fxx multiplied by fyy minus fxy getting squared. Once you form D, step 3 is you're going to evaluate D for each critical point and then apply the theorem, which is the D test. And distinguish if you have, you know, max, or do you have a min, or do you have a saddle point, or, you know, maybe the test is inconclusive. So this is the procedure for you to follow, and I'm going to put you in your room for, let's go for like 7 or 8 minutes. I want you to work quickly, okay? Don't sit there and dilly-dally and, you know, go, hey, how's your day, and, you know, how's your mother, and what are you doing this weekend? Just get to it, all right? So we've got 19 people in the room, or now we have 20. No, wait, okay, so we have somebody else just joined us, whoever just joined us. Good morning, good morning. Okay, so we're going to put you in some groups here, and then when you get invited to your group, go in there and have fun. Bye. I need to start that recording. Okay, so the saddle point and the rel max, we're gonna see if we can find it. So here we go. So this is a nonlinear system of equations, and it's nonlinear because, of course, this x squared term is the nonlinear term, and that makes the whole system nonlinear. So what's the best way to solve it? Well, the best way to solve it is by substitution, using the substitution method. So you pick which one of the equations you want to do business with. Usually this the more easy of the two, because you're going to solve for one of the variables. So I chose this one, and when I chose this one, I solved for, and it's up to you because it's about equally the same, I solved for x, and I basically got x was equal to y. Did you guys get that?
Yep.
Yeah.
And then I substituted that back into the original equation. So you go back way over here, and I go, okay, so then the second equation, when you put a y there in place of the x, you have this, negative 3y squared plus 4y. And that's an algebra problem. It's a quadratic equation. And please know how to solve quadratic equations. I've seen people, this is what not to do. Please don't do this. If I see anybody do this kind of stuff, this kind of funny business on an exam or a quiz, I'm going to get real unhappy. So I've seen people where they go, oh, okay, well, I'll add 3y squared to both sides, and then I'll get 4y equals 3y squared, and then they do something illegal. They divide both sides by a variable. This is illegal, and what will happen is you will kill off some info. You'll kill off a solution. It's and the reason why is because it's illegal to divide or multiply both sides of an equation by 0. So don't do that. Well, then how do you do this? Well, you could use the quadratic formula, because this is a quadratic equation, but that would be overkill, because you don't need to do that. Instead, factor out a common factor, and then after factoring, apply the ZPP, the zero product property, and it's very easy to solve. So then what am I going to have here? Well, the ZPP says if something times something is equal to 0, then each of those factors can individually get set to 0, and then you solve for the variable for, well, this one's already solved. Okay, y is equal to 0, that's one of the solutions. And then here, if I add 3y to both sides and then divide both sides by 3, I get y equals 4/3. Now, folks, you have to be careful, because 0 4/3 is not the critical point, okay? The critical points, and there's 2 of them, one of them has a y coordinate of 0, and the other one has a y coordinate of 4/3. Now, how do you get the x coordinates for those critical points? Well, you go back to your system of equations, that was way back here, and you could just plug either of those the y coordinates into any one of those equations. But look, why don't we use the simple fact that we've already solved for x in terms of y? Why don't we use that? X is supposed to be equal to Y. So if Y is 0, X must be 0 also. And if Y is 4/3, well, I guess X is 4/3 also. So I'll give you partial credit on a problem if you at least get the critical points. That's good news. So, but we have to finish the problem. So you need to go get D and perform the D test on each of these critical points to see what it is. So if, so this is example 3, continued. The D is fxx times fyy minus fxy squared. So the D for this problem ended up being what? Negative 6x multiplied by fyy, which was negative 4. And then I believe fxy was just a constant. It was 4, so then you square it. I'm just going to clean the D up a little bit by simplifying. There's my D, 24x minus 16. So if I test the point 0, 0, and so I evaluate D at the point, the critical point 0, 0, I get a negative number. Oh, holy smokes. What does that mean if your D is negative? Go look at the theorem. Saddle point. Saddle point. So, and folks, a lot of times I like to see the order triple. So the order triple, the point on the surface is 0, 0, and then the function evaluated at 0, 0. And it turns out for this function, if you substitute in the point 0, 0, your z coordinate on the surface is 1. So that's one of the answers right there. I have a saddle point, and so you can kind of look at the picture of the surface, because I drew it, and you can see that right there, that's supposed to be at the point 0, 0, 1, right there, where there's a saddle point at the point 0, 0, 1 on the surface. Yep, that looks like right there, there is a saddle. I'll buy it. So that's just validating one of our answers. And now if I test the other critical point, 4/3, 4/3, what happens? Well, when I evaluate D at this point, substitute it in, I get 24 multiplied by X, but that's 4/3 minus 16. And you can do some reducing. 24 divided by 3 is 8. This is 32 minus 16. I don't even, a lot of times I don't finish out my D because I kind of get a little lazy, and I'll let you also. I mean, this is obviously a positive. It's like, okay, yeah, all right, positive, fine. So now what? Well, the theorem says if D is positive, you aren't sure. It could be a max or a min. So what is it? Then you have to evaluate fxx at your critical point and see if it's positive or negative. And it turns out it's negative. Yeah. And why is that? Well, because fxx was equal to what? Negative 6x. And if you plug in your 4/3, this is going to be a negative number because a negative times a positive is negative. So what can you conclude when your D is positive but fxx is negative? And if you look at the theorem, it's a relative max. And so the ordered triple for this relative max, the point on the actual surface, would be 4/3, 4/3, and then f evaluated at 4/3, 4/3. And if you actually punch that up, it's not going to be pretty. That z coordinate is 59/27. I know, weird. But I think that you can appreciate that it does look like there's a max right there at the tippy top of that little peak. That's a relative max. Okay, so any questions on this cool problem?
Why didn't we get that other max in the graph?
What other max are you referring to?
So does that one extend up indefinitely?
Yeah, that goes up forever and ever.
Oh, okay, okay.
Showing, yeah, this surface that I'm sketching here is simply a portion of the whole surface, because I don't know if you can see my screen, George, but see over here where my parameters, my X, Y, and Z are kind of limited to a small region.
I see it.
Yeah. So it's not going to graph the whole shebangy. This surface goes on forever in all sorts of directions. This just gives you a portion of the graph. Now, if we were finding absolute extrema on a region in the XY plane, then I would say you would get an absolute max. So you could get an absolute max because you can see that, I'm just zooming out a bit, that there are portions on the surface that are higher than your relative max. That's why we call it a relative max, right?
Yes.
Okay. So any other questions? These are good. Okay, so I'm going to do lots more examples today, so it's just going to get harder and harder. And when I say harder and harder, what I like to do is I like to pick different flavors for you that involve different linear systems that are pretty intense. Like some of these linear systems are much more challenging than the ones that you saw in your pre-calc, and yet I expect you to know how to handle it. So I want you to see them. So this is a classic problem, and when I say classic, I mean that every single calculus book that I have on my shelves here, and you don't see down here, but I even have more down here. There's a lot of them. They all have this problem in it or a flavor of it. So be on the lookout for that to occur on a quiz or exam. Hint, hint. Okay.
Professor, we still have example 4.
Did I skip example 4? Uh-oh. Yeah. Oh, we got to do example 4. Sorry. Oh, yeah, we got to do this one. All right, this is kind of a classic also. Thank you for pointing that out. Vanessa, are you in the room?
Yes.
Example 4 isn't as ugly as you think, Nicholas. Don't worry. And Nicholas S., we're going to do example 4. So, Vanessa, the problem that you asked me about prior to class that's in my math lab, one has that flavor to it. You'll see in a moment. Okay.
Okay.
So keep your eyes open. I wanted to do this before you do that. So I'm going to go get fx and I'm going to go get fy. So I want you to notice that my Microsoft Surface Pro is acting weird. I have no idea why. That is very strange. I'll go up. Yeah, I don't know why it's. Interesting. Okay. All right, so fx, see if it's happy now, I don't know, is 4x cubed minus 32. And I'm going to just preemptively set it equal to 0 because I know I'm going to need to. And then fy is 5y to the 4th minus 5. And I'll preemptively set it equal to 0. Now, folks, this is a nonlinear system of equations. Here is the difference between this nonlinear system and the one that you just did and the one I did on Wednesday. The other two examples that we did, both equations had both variables in it. They both had x's and y's. If you'll notice here, the difference is that each of these partials has only a single variable in it. Does everybody see that?
Yes.
And that means different flavor of how you're going to give the solution to the system. So please, I'm begging you, pay attention to this other flavor. So you're going to get a solution to the first equation, and it's going to be x's. So here, if I add 32 to both sides, I'll get 4x cubed is equal to 32. Okay, divide both sides by 4. Okay, then I get x cubed is equal to 8. Now I'm going to take the cube root of both sides. Do I need a plus or minus if I take the cube root of both sides of an equation?
No.
No, I do not. Why not?
It's an odd root.
Good. And I'm going to test you on this fact for the next couple quizzes and the midterm and the final. I like to find out who knows this pretty basic and simple fact that if you take an odd root of both sides of an equation, you don't need a plus or minus. However, if you need to take an even root of both sides of an equation, you must have the plus or minus. Otherwise, you're going to lose lots of info. So here, no plus or minus, you just get x is equal to 2. Okay, fine, save that for later. Then this other equation, we're going to solve it for y. I'll add 5 to both sides. I'll divide both sides by 5. I'll get y to the 4th equals 1. Now I'm going to take an even root of both sides of an equation. What does that mean?
Plus or minus.
You better put a plus or minus, you betcha. Because you get two answers. Y could be plus or minus 1. Now, for those of you that took differential equations or are taking differential equations or plan on taking differential equations in the future, may I please interject something here at this moment when it comes to mathematics and solving polynomial equations. And you probably already studied this fact in pre-calc anyway, so I'm reminding you. When you solve a polynomial equation, and then we just solved two different ones, this one and this one, the number of solutions will be exactly equal to the degree of the polynomial equation. And so in the first equation, 4x cubed minus 32, it looks like when we did it, we only got one answer. Hey, you're lying. You said there were three answers. I claim there are three answers, but the other two for this one are complex numbers. And in this course, I don't want to even acknowledge the complex solutions because we stick to functions of a real variable in this course. However, when you go on to take differential equations, you will be held accountable to get all three of those solutions. This one is the pure real answer, and then the other two are complex. And if you don't, you will fail differential equations. Congratulations. Okay, now similarly for this fourth degree polynomial equation, it looks like, oh, you lied, we only got two answers. You said there were four. I claim there are four, and the other two are complex. These are the two real ones. Real numbers are complex, of course. I'm just saying pure real. And so we're not going to even look for the other two solutions because we're sticking to just functions of real variables here. But if you're taking differential equations, you better get all four, okay? And it's important that you understand that distinction, okay? Now I'm going to get off my soapbox and let's move on. What are your critical points? At this point, you're going to mix and match. Now, you don't mix and match all the time, okay? Like the last two examples where you did one and I did one on Wednesday, there was no mixing and matching. Once you got an x coordinate, you had to find the corresponding y, or vice versa. Once you got your y, there was a specific x that was key to that. Here, because this system of equations was not like the true system where you had a mixture of x's and y's in both of the equations, where you had one that just had a single variable and the other one had the other single variable, this is where you get to do your mixing and matching. So what the heck do I mean by mixing and matching? You look for all the possible combinations that x and y can make with each other to get all your critical points. Yeah! So x is 2, and y could either be 1, or x could be 2 and y is -1, and we're done. And those are two critical points. Now, just a little aside, because I do give you harder problems, what if you got two possibilities for x? Let's just say x was, I'll just make something up. Let's say x could be plus or minus 10, and then y could also be plus or minus 11. Then you have to do all the possible permutations. So you'd have like 10 positive 11, 10 negative 11 would be a critical point, and then you'd have -10 positive 11 and -10 negative 11, and then you'd have 4 critical points, and then you'd have to do the D test 4 times. Is that clear what I mean by this idea of mixing and matching?
Yes.
Don't do it all the time. Like I have students who don't listen to me, or they only listen, you know, with half an ear open, and then they hear, oh, mix and match, and then they go mix and match every single relative extrema problem, and I just give them zeros all across the board because that's not the point. Okay, so now I got to go get my D for this example. Oh dear. So I go, what is fxx? So if I go up here to fx and take the derivative of fx with respect to x, I'll get 12x squared. Then I'm going to multiply that by fyy, and if I look at fy and get the derivative of that with respect to y, I get 20y cubed minus, and now I got to do fxy squared. Well, if I take the derivative of fx with respect to y, there's no y's in there. So that's going to be a big old 0. So 0 squared. So there's your D, and now you have to do your D test twice. So D evaluated at the point 2, 1, I claim is you're going to basically get a positive times a positive number, which is equal to a positive. I don't even care what the numbers are sometimes. This is like, I just care if D is going to be positive. And that means I'm going to either get a max or a min. So now I have to look at fxx. But notice that fxx is 12x squared. So it's going to be positive regardless of the values of x and y. So when both d and fxx are positive, that means that the function has a relative min. And so that point gives us a relative min. And I usually like to see your ordered triple. So what would be the z coordinate for that minimum? And I claim it would be -60 if you plug in this coordinates. And now if you do the d test for the other critical point, 2, -1, you're going to notice that, well, when you plug in the point to 12x squared, you'll get a positive. But if you plug this point into 20y cubed, you're going to get a negative. But a positive times a negative is a negative. So in other words, it's going to be less than 0. And that means we have a saddle point at this other point. And then the ordered triple is 2, -1. When I plug in the point 2, -1 into the original function, I get -52. Okay, and we're done with this problem. So this problem has a little different flavor. So I want you to get this whole idea. Okay, questions?
I'm good.
No questions.
Okay, so now we're ready for the big old classic. This one's standard fare. Okay, so so getting fx and fy and setting them equal to 0. Okay, so how hard could that be? Not hard at all, because you guys know how to take partials. So when you take the partial of 4xy minus y to the fourth minus x to the fourth with respect to x, I think I'm going to get 4y minus 4x cubed. That look right? Equals 0.
Yes, that's right.
Yeah. And then if I take the other partial with respect to y, 4x minus 4y cubed. Okay, that's going to equal 0. Okay, nonlinear system. Definitely nonlinear. So both of these equations have about the same challenge level as far as choosing which one to solve for the other variable. So it kind of doesn't matter which one you decide to go with. I'm going to, what the heck am I going to do? I don't know.
The Bob one is actually a bit easier.
Really? Okay, what do you want to solve for then?
Solve for x.
Okay, all right, we'll do what Nick wants. Okay. All right, Nick, you're up. So what is my x going to equal?
That's going to equal y cubed.
Good. So then substitute this into the other partial that we didn't use. That would be fx. Okay, so if x is equal to y cubed, then I'm going to go like this. And this is the part where a lot of students blow it because they forget their exponent laws. So what happens when you have a power raised to a power? Do you add, subtract, or multiply those exponents with each other?
You multiply the exponents.
Good. Thank you. And that's key. So now you're going to factor and apply the ZPP in order to solve this polynomial equation. So I'm going to factor out a common factor to both of those terms. I think 4y is a good bet. And then I'll have 1 minus what?
Y to the 8th.
So Adriana, I saw your chat box thing. I'm going to say you have part of the answer, but not all. So now when I apply the ZPP, I say if something times something is equal to 0, I set the first factor equal to 0 and the second factor, and baboomba, I have to get my y coordinates for my critical points. So here, if I divide both sides by 4, I get y equals 0. That's one of them. Here, if I add y to the 8th to both sides, okay, then what? I'm going to take the 8th root of both sides of the equation. But what do I have to remember when I take an even root of both sides of an equation, folks?
For minus.
Plus or minus, baby. So plus or minus the 8th root of 1, and we're just going to go for the real answers only, because ordinarily this would have 8 solutions, right? Hello?
Yeah.
Yeah.
Yeah, you get 8 solutions. I'm not making this up, like for realsies. total. But we're not going to go for all 8. Good news. But if you take differential equations, they're going to want you to get all 8. Okay, now here we got 2 of them. Hey, 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 hey. The 2 pure real ones. The other ones are all complex. All right, so we don't care about those other 6 solutions. Fantastic. Go get them on your own. All right, now what? Well, look, what do we have? We've got 3 critical points total. One of them has a y-coordinate of 0, one of them has a y-coordinate of 1, and the other one has a y-coordinate of -1. How are we going to get those x-coordinates?
You have x already, basically. X is equal y cubed.
Yes. So use it. So if y is 0, 0 cubed is 0. If x equals y cubed and y is 1, 1 cubed is 1. And if x equals y cubed and y is -1, you get a -1. All right, that's nice. So there we go. Those are 3 critical points. Oh man, that means we got to do the D test 3 times. Oh yeah. So D, got to go get your D. Fxx for this problem. Okay. If fx is 4y minus 4x squared, cubed rather, the fxx will be -12x squared, and then you're going to multiply that with fyy. So look at fy, it's 4x minus 4y cubed. What is the derivative of that with respect to y?
-12 or -12y squared.
Minus, now we're going to do fxy getting squared. What is fxy? You look at fx and you take his derivative with respect to y. I believe you're just going to get a constant, 4. So if I clean b up, here I have a negative times a negative. That's going to be positive 144x squared y squared minus 4 squared, but that's minus 16. So here's the d that we're going to do business with. And we're going to have to use it 3 times. So here we go. Let's test the 0, 0. So when you evaluate the d at 0, 0, which is pretty easy, you're going to get -16, which is a negative value, and so you're going to have a saddle point, because the theorem says if d is negative, you have a saddle point at the ordered triple 0, 0, 0. If you plug in your 0, 0 into the original function, which is up here, 4xy minus y to the 4th minus x to the 4th, you'll get 0. So you got a saddle point. Okay, what about the point 1, 1? What happens when you evaluate d at 1, 1? Well, you're going to get 144 minus 16. I don't even care what the number is. I'm not even going to whip out the calculator, people. I'm lazy. I think we all can agree that's some positive number. That's all we care about. We want to care about the sign. Then what? Well, if d is positive, we may have a max or a min. It depends. What's fxx doing? Well, if you evaluate fxx at the point 1, 1, I get a negative number. Ooh. What happens if d is positive and fxx is negative?
And the maximum.
Max.
Relative max. Yeah. And that relative max occurs at the ordered triple 1, 1, 2. So the max value, the relative max value, it has a z coordinate of 2. And then finally, let's test -1, -1, and it's going to turn out that -1, -1 is also going to have d be positive, and fxx evaluated at -1, -1 is, I have no idea what's happening, is going to also be equal to a negative number. And so we have another relative max. Is that even possible? Yes. So you'll have -1, -1, and I think the z coordinate is also a 2. And we're done with this problem. So those are all the things that are happening with this function. Any questions or comments?
I like these problems. They're
You
fun.
like them? I know,
Yeah.
they're fun, aren't they?
Yeah, they're the right mix of mechanical, but you still have to think about it.
And I claim it is very satisfying to get, your answer. Of course, if it's right, what if it's not right? Well, it's a little disappointing. Then you have to go and do a little bit more algebra or check your algebra. That might be the problem, is your algebra might be yucky. But let's just see what this puppy looks like. Ooh, wow, that's kind of cool. Can everybody see that we have a saddle point right there at 0, 0, 0?
Yes.
And you see how we have two relative maximums there? Yeah, that looks like it's about right. Cool. I'm sick of candy stripes. Let's do something else. Mauve. No. How about rainbow? Ooh, that looks pretty. Okay, yeah, let's go black and white. Checkers. Oh, checkers. Nice. Okay, enough fun. Back to work. All right. I got to take my fun where I can get it. All right, now we're going to do a problem that some of you may not appreciate too much, but I like it. And I put similar ones in your homework, so enjoy. So here's another flavor. You know me, I got to give you the flavors. This is not a polynomial like all the other examples we've done. This is an exponential. Yeah. How do you deal with it? Well, carefully. So how do you get partials? Well, how do you take the derivative of an exponential? You guys know from Calc 1 that if you take a derivative of e to the u, you're going to have e to the u times u prime. And so we're just going to use that exponential rule, but we're going to use it in the context of partials. So here we go. The partial of f with respect to x is going to be the whole e to the blah, blah, blah. And if you don't mind, I'm going to get really lazy. E to the blah, 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 that whole thing. I don't feel like writing it all out. You know what it says. Times the derivative of blah, 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 but with respect to x. So what is the derivative of x squared minus y squared minus 2x minus 6y minus 3 with respect to x?
2x minus 2.
And so that's going to be the factor there. And I'm going to set that equal to 0. Okay, fine. Now when I take fy, I'll still have e to the, you know, whatever. And now I'm going to multiply that by the derivative of x squared minus y squared minus 2x minus 6y minus 3, but with respect to y. Can we get lazy on our tests? Isaiah? Absolutely. Just go blah, blah, blah like I'm doing on this one. Now, there's some where I don't let you get lazy, okay? Let me put this on pause for a second. My goodness. So when I get my partial with respect to y, I think I'm going to get, negative 2y minus 6. All righty. And I'm going to set that equal to 0 preemptively. All right, fine. Now, folks, we have definitely a nonlinear system of equations here. Oh, my goodness. But here is where the ZPP is going to save your rear end. And I mean save your rear end. The ZPP, the zero product principle or zero product property. So it basically, you want to use it whenever it's appropriate. And so folks, I already have, with the fx, I have something times something is equal to 0. Right there. So I can actually write this down. 2x minus 2 has to equal to 0, or e to the blah, blah, blah has to equal 0. Yeah, I know that seems pretty funny. But folks, this has no solutions. How do I know this? Well, I happen to know that e raised to anything is always positive. It's always a positive result. Go ahead and graph an exponential and you'll see it's always positive. But if you don't buy that, well, I'm not going to buy it graphically. Show me analytically. Sure. How do you solve an exponential equation? You take the natural log of both sides. Does everybody see that if I took the natural log of both sides, do you see that the natural log of 0 isn't even defined? I hope you agree to that. Hello?
Yes.
So this has no solution. So it doesn't help us out at all. So he's out. So what about this? Well, here, when you solve for x, I get x equals 1. Okay, save that for later. Now you're going to look at the fy. So you're going to apply the ZPP, the zero product property, use it again. It's awesome. It basically says the negative 2y minus 6 has to equal 0, or, it's a negative there, the e to the blah, blah, blah has to equal 0. I think we already agreed that this thing here is always positive. It's impossible for e to the blah, blah, blah to equal 0. There's no solutions. However, over here, if you add 6 to both sides, you'll get y equals -3. So there's only one critical point for this problem anyway, and it's located at 1, -3. Now, go get whether it's a max or a min or what the heck is it. Now, this is where you're probably going to hate me, but I need to go get D. So what the heck is D? So for fxx, let's do these separately. So I'm just going to get fxx, fyy, and fxy separately because it's going to be kind of long. Fxx is going to need the product rule. Why?
Because it's two functions of x.
Yeah, so you're going to go, all right, so you're going to first take the derivative of 2x minus 2 with respect to x, and that's a 2, and then times the g, that's e to the blah, 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 plus, and now you're going to take, well, the 2x minus 2 stays itself, and then you're going to take the derivative of e to the blah, blah, blah with respect to x, but that's e to the blah, blah, blah times 2x minus 2, okay? So there's fxx. Fyy, you're also going to need the product rule, because it's also a product of two factors involving a y. So when you take the derivative of -2y minus 6 with respect to y, you'll get -2, and then times the other factor, e to the blah, 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 plus, and then you'll still have the -2y minus 6, and when you take the derivative of e to the blah, blah, blah with respect to y, you'll get e to the blah, blah, blah times the derivative of the exponent with respect to y. Okay, fine. Now, fxy, good news, you don't need the product rule because that's not a product of two things with respect to y. So you'll just have the 2x minus 2 as a constant multiple, and then the derivative of e to the blah, blah, blah with respect to y, we've already done that, is -2y minus 6 e to the blah, blah, blah. Okay, now I'm going to sort of just walk through this. When you evaluate D at the critical point, what are you going to get? All right, so when you plug this point into this fxx, what are you going to get? Well, I hope you can see that this second term, when you plug in x equals 1, do you see it's going to go to 0?
Yes.
So you're just going to have like 2 times e to the blah, blah, blah. But remember, e to the blah, blah, blah is always positive. So you're just going to basically get 2 times some other positive number, e to blah, blah, blah. And then you're going to multiply that by fyy evaluated at the point 1, -3. And I hope you can see that if you plug in y equals -3, this term, this second term of fyy goes to 0. So you only have to worry about the first term, and that's going to be -2 times something positive, okay? And then you're going to go, all right, minus fxy getting squared. Okay, what the heck? When you plug the point 1, -3 into fxy, it goes to 0. So I hope you can tell that for this problem, and we're kind of doing hand waving here, this number here is going to be negative. And so this is going to be a saddle point for this particular function, and I'm done with the problem. I don't want you want to find the order triple. Now I do want to warn you, because a lot of times when students see a problem done in lecture, they go, oh, every single problem that I do where it has an e to the blah, blah, blah will end up with a saddle point. Yeah, that's the ticket. And if you just fell into that death trap, I feel sorry for you, because that's not the case. That's for this problem, it did end up being a saddle point. So be careful. Sometimes you may get a max or a min. Okay, show the second partials test fails. This is easy peasy to go do, folks. If you get fx, you'll get 2xy squared, set it equal to 0. If you get the partial with respect to y, set it equal to 0. Now, folks, this is where students fail. Be careful, because a lot of students look at this and they'll go, oh, the point 0, 0 is a critical point. I will agree with you and I will disagree with you at the same time. And the reason why is 0, 0 is indeed a critical point, but I claim there are actually infinity critical points. So 0, 0 is one of an infinite number of critical points. Well, what do you mean? What other infinity critical points are there? Well, let's think this through. Think about it. Like, here's the xy plane. Okay, 0, 0 is definitely going to give us a critical point. But what else? What if we were on the x-axis? And you guys know if you're on the x-axis, whoops, that y is equal to 0, whatever point you pick. You know, your y coordinate will be 0. plug any other, let's just say this point right here, 10, 0. Plug the point 10, 0 into this system. Do you see that it makes both of those equations go to 0? It
Yes.
will.
Yes.
So every single point that lives on the x-axis, and there are infinity of them, are also critical points. Ha ha ha. And then similarly, I claim the entire y-axis, which has the equation x equals 0. Any of those points, you plug them into this system, both of those partials go to 0. So there's even more infinity critical points. Well, how is that possible? And it turns out, I'm going to try to sketch this by hand. It turns out that you guys know what rain gutters are?
Yeah.
Yep.
You can kind of think of rain gutters being along both the x and y axes. You know, you've got minimums essentially along both of the axes. So you can't do the D test because the D test is going to fail. Because if you try to get fxx and fyy and fxy, you're just gonna, and then plug in the point 0, 0, you'll just get d equals 0. And but that doesn't mean there aren't, you know, in this case, minimums all the way along. Now, example 8 is kind of hokey. Sometimes I give this as a freebie points on a quiz, and sometimes I'm nice like that. And I pulled this out of a business calc book. When I teach business calc, they do this topic right here. They find relative extrema. So if they give you the fact that x naught, y naught, they're telling you it's a critical point. So good news, you don't have to go find the critical point. And then they're telling you the values of these second partials. When you form D, which is fxx times fyy minus fxy getting squared, by virtue of looking at your D and then also your second partials, you can tell whether or not this is going to give you a max, a min, or a critical point. What do you think?
That's a max.
That's a max. Good. Real max. How do I know without graphing, Adriana? You would have to graph it. And I just gave you the graph, okay? So, but you're not going to be asked to do that on an exam. Okay, Adriana? I hope that answers your question. I'm not sure. Okay, good. Yeah. On tests, I'm not going to ask that you have your browser open with a 3D grapher and then you're going to be frantically graphing, you know, explicit or implicit functions. You won't have to do that on any of my exams or quizzes, okay? I do that for you in class just as a favor so that it'll help you visualize the stuff that's going on. No worries, Adriana. I'm sorry it's loud at your house. You got a zoo going on there? Oh dear. Okay, so let's do the grand finale before I do some optimization. Yes, I'm not done with you yet. This is a hard problem. And yes, you're going to have ones like this where you have to think a little bit differently. So it's one of the most advanced nonlinear systems you're going to get. So this is like the hardest of the hard. So it has a different flavor than all the other problems I've done so far, okay? And it's not as fun because there's no e to the blah, blah, blah. Okay, here we go. First up, find fx. Ooh, shoot, okay. Good Lord, I think it's negative 6xy minus 6x. Okay, set it equal to 0. Then find the other partial with respect to y. I got a 3y squared for the first term, and then a minus 3x squared for the second term, a minus 6y for the third term, and I think that's it, and set that equal to 0. Okay, this is definitely a nonlinear system. It is hell. Oh my goodness. And this is where it gets hard. Now, I want to say something right now, because sometimes people start doing stuff, and then they go off on the weeds, and then they spend 5 pages doing the, I've actually seen this. Like, I put this problem on a take-home quiz when we were still face-to-face, and I've seen students turn in, like, this problem alone, like 5 pages. There you go. And it's just one. And, you know, and the fact that a student even thinks that I'm that heartless and cruel that a problem would even take one single problem 5 pages kind of breaks my heart, actually, that you would think that I would be that evil. Now, not that I'm not evil, I resemble that remark, but I'm not that evil. Okay, so folks, if you find yourself going off and a problem is just taking tons of paper and you're like, oh my God, this is ridiculous. Well, that's Rasky. No, that's not Rasky. Okay, you're blowing it. So don't use the substitution method on this, because if you try substituting the substitution method, let's say here you solve for x or whatever, and you plug to the other, you're going to get some disaster zone from hell. And I've seen people actually just keep going, like, oh yeah, this must be what she wants. Oh, okay, all right. So no. So here's the plan here. You're going to apply the ZPP. This is going to save your rear end, people. So what do I mean? Look at this equation. Can you see that the common factor, let's pull out a common factor of -6. Yeah, that's the ticket. And when I pull out a -6, the other factor is going to be y plus 1. Okay, fine. How does that help? Well, then you got something times something equals 0. So you go, oh, okay, that means the first factor equals 0, or the second factor equals 0, or hell, maybe they both do. And so then when you solve for these, I get x equals 0, or this isn't an and. This is not an and. Y equals -1, okay? This is not an and, so be careful. This is where the different flavor comes in. I'm helping you out, peeps. You won't have seen this in a pre-calc class. What you're going to do to get the critical points is you're going to substitute one of these into the other partial and see what the corresponding y values could be. So if x is equal to 0, then your fy looks like, what the hell does it look like? Oh my goodness. It looks like 3y squared minus, and then when you substitute 0 in place of x, you get 3 times 0 squared, minus 6y equals 0. But then this just looks like 3y squared minus 6y equals 0. Okay, fine. And then when you pull out the 3y, you get y minus 2. And now you use the ZPP again, and then that says 3y equals 0 or y minus 2 equals 0. Or maybe they both do. Okay, fine. And then you're going to go, okay, y equals 0 or y is equal to 2. Okay. So what are we saying? We're saying that when x is 0, y could either be 0, or when x is 0, y would equal 2. Well, how come y isn't equal to -1? Because that won't make both of the partials simultaneously equal to 0. So the point 0, -1 is not a critical point. Don't even go there, because it's not going to make both of these equations go to 0. That means you're losing sight of what it means to solve a system. A solution to a system means that when you plug in that one point, it solves both of the or satisfies both of the equations simultaneously. So these are two critical points. Then what? Then you examine the other guy. If y is equal to -1, then fy looks like what? So when you substitute -1 for y into your fy, x just stays x, and you get this, but that's 3 minus 3x squared plus 6 equals 0. And now I'm just solving for the x, and so then I get x squared is equal to 3. And then when I square root both sides, please remember your plus or minus here, otherwise you're going to lose it. And I get x can be plus or minus the square root of 3. So then what? So the other critical points are square root of 3, -1, and negative square root of 3, -1. I have 4, count them, 4 critical points. Oh my God, that's nuts. Well, what then? Well, I don't have time to do the D test on this, but you should, or you're going to have to. Don't skip those steps and tell me, oh, I'm tired and I don't like writing. So the D test tells us that you're going to have a rel max at the point 0, 0, and then the z coordinate is 1. And you're going to have 3 saddle points. So all the other guys are saddle points, okay? So one of them is at 0, 2, -3, and the other ones are plus or minus square root of 3 was the x coordinate, a -1. It turns out that both of those saddle points have the same z coordinate. That's why I'm kind of doing shorthand here, okay? So that is that problem. Fun times. Okay, now let's go to optimization. So what is the application for finding Extrema? I know it's really fun to go find Extrema. I have fun with it. But, you know, engineers and business applications, you can use it to find maxes or mins. And that's the point. So we're going to find a max volume. So this This problem is classic. Well, Briggs doesn't think it's classic, but whatever. So this is this is kind of a cool problem. Let's say you have the XYZ coordinate system, and you're trying to figure out how to maximize the volume of a box. And it's sitting on the ground, where the ground is your XY plane, where one of the vertices here is at the origin. And the opposite vertex lies in this plane. And you guys remember how to graph planes? You figure out the x-intercept, so you set y and z equal to 0, and I get 4 as the x-intercept. To get the y-intercept, you simultaneously set x and z equal to 0, and I get 6 is the y-intercept. And the z-intercept is 8. And then here's the portion of the plane anyway. So the opposite vertex of this box lies in that plane. And then if I actually try to draw the box, don't judge here. I'm trying to draw something in 3D on a 2D thing here. Oh God, that looks terrible. Okay, can you imagine this box right here? So you're trying to maximize the volume of that box, where one vertex is here in this plane and the other vertex is at the vertices at the origin. So you know that volume is XYZ. You want to maximize this. But here's the problem. You've got 3 variables, not 2. And I only taught you how to use the d-test for a function of 2 variables. So it's like, oh, shoot, what do I do? Well, you use this secondary equation. This is not the equation that you try to maximize, okay? You use the secondary equation to solve for z, and then you'll substitute that z into the equation of the quantity you're trying to optimize, in this case, the volume equation. So it turns out after I solve for z, and you know, just use some algebra here, subtract your 6x and 4y from both sides and divide both sides by 3, you're going to substitute this into the volume equation. Great. So your volume equation is going to look pretty disgusting. I know. Like this. And then what I do before I take my partials, I leave the 1/3 out because fractions irritate me, but I will distribute the xy. So it's going to look like this. Okay. And now I'll go get my partials. So I need to get Vx and Vy, and then I'll simultaneously set those to 0 and try to solve the nonlinear system. Okay. So the 1/3 is a constant multiple, so copy it down, and then the derivative of this huge expression with respect to x is 24y minus 12xy minus 4y squared. Before I set this equal to 0, if you don't mind, I notice that all 3 of these terms have a common factor of y, so I'm just going to factor out the y just to make it a little easier to look at. And then you know what's going to happen. The ZPP, baby, is going to save you. That ZPP is gold. And then the similar technique you'll use here for the other partial, you'll have 1/3 times the derivative with respect to y. So I get 24x minus 6x squared minus 8xy. Oof. And I'm going to a common factor of x. I'll just factor that guy out. So I'll have x over 3 multiplied with the quantity 24 minus 6x minus 8y. Okay, now here's the part where I'm going to kind of hand wave us through here. If you look at both of these equations, this is definitely a nonlinear system of equations. Oh, goodness. I hope that you notice for the first equation, if you apply the ZPP, y equals 0 is definitely going to happen, and then the rest of the mess set equal to 0. And then with the other equation, when you set both of those factors equal to 0, you get x equals 0. So it turns out that 0, 0 is a critical point. Okay? But it's not a critical point that I care about in this real life application. Now, you're not allowed to just discard critical points. So don't use this technique because I'm going to ignore 0, 0 for this real life problem. But like any of the other generic problems that we did, you know, when you get 0, 0, you're not allowed to go, well, that's not interesting. No, you can't discard it. That could be the guy. The reason why in this real life application that I want you to get that it's okay is because x is essentially your width, y is your length, and z is your depth or your height of your rectangular box. And if you had x and y be 0, would that be maximizing your volume, people?
No.
I don't think so. In fact, you would have a flattened out box.
Envelope.
Yeah, you have an envelope. That's not fun. So we're going to ignore this critical point because it's a real life problem and we can, and we get that 0, 0 is not going to be a max for this volume. So we're going to go, forget that. So what we're going to focus our eyeballs on is what's left after we sort of kill off those factors. And I claim that if you look at what's left, you have a linear system of equations. Oh, happy, joy, joy. Because, you know, any self-respecting algebra student, you know, beginning algebra, I'll rewrite these where I put the variables on one side and the constant terms on the other. So this looks more like the way they present a linear system of equations to a beginning algebra student, okay? Yeah, diet box, thanks, Nick. Okay, now in this situation, because it's a linear system, you can use either the substitution method, that always works, or if you prefer the elimination method, I'm okay with that. What I did for my problem is I multiplied both sides of equation 2 by -2. So it looked like -12 minus 16y equals -48. And I kept the first equation the same, so I'm just going to copy him down. And then I added these two equations together. You know, you've seen this before, right, folks? Please say yes. And so that allowed me to eliminate the x variable, and that's why they call it the elimination method. And then I can solve for y here. So y is equal to 2. Now, how do you get x? Well, I could back substitute y equals 2 into either one of these original linear systems here. Doesn't matter which one. How about the second one? 6x plus 8y, but y is equal to 2, is equal to 24. That'll give me 6x is equal to 24 minus 16, which is 8. And I get x is equal to 8/6, but that reduces to 4/3. So now the critical point that I have in hand has an x coordinate of 4/3 and a y coordinate of 2. Now at this point you could go, I've got it, I'm done, that's going to maximize volume. But I'd like you to prove it to me. Like, don't just go, yeah, that's a max, because I have good intuition. So at this point, prove this gives a maximum volume. And I mean like prove it. Like fact check it, you know, the real deal. Well, how do you do that? Well, you got some work to do. You're not going to like this, but you're going to have to go get the D. Oh, no. So you're going to go get Vxx, which is equal to -4y, and then you'll go get Vyy, which I claim is -8x over 3. You know, and I'm going back to the original Vx and the original Vy's right here in order to get my second partials. You can't go to the abridged version where we killed off some factors. That's not legit. And then the Vxy is equal to, you're not going to like it, 1/3 times the quantity, 24 minus 12x minus 8y. So if you want, you know, when you put your D together, which is going to be Vxx times Vyy minus Vxy squared, and when you evaluate the point 4/3 2, your Vxx is going to be something negative. So I'm just going to go like negative. Times, you know, and then you're going to get here, you're going to get something also negative. So you're going to get, you know, this is, I think this one is going to be -8, and then this is also something negative. I think this is -32/9. And then minus, and then when you plug in your point here, this is going to be terrible. You're going to get -64/9. Oh, good Lord. And then that's going to end up being 64/3, but that's positive. Okay, that's good. But the Fxx is negative when you plug in that point. And so together, this tells me by the theorem that I do have a relative max, which is what I was looking for, thank goodness. And so that indeed is the max. Now, we didn't answer the question. And this is the part where students neglect to finish out the problem. They're like, yay, I'm done. And it's like, no, you're not. Like, you didn't give all the answer. Well, what do you mean? Well, look what they wanted. They wanted the dimensions of the box. So you gave me part of the answer, like you told me the x length here, this width, is, you know, 4/3 units, whatever the units are. And we got the y. Okay, great. That's 2 units. But what about z? You know, how tall should the box be? You better tell me, because, you know, they also ask for the actual max volume, so you didn't give all the stuff. So the z, there's 2 ways to find the z. You have your restriction there that the z value has to lie in that plane. So you could plug your x and y into the plane equation. But remember, you use that plane equation to solve for z. So I would plug x equals 4/3 and y equals 2 into, you already solved it for z. And when you do that, you will get a z, this is the depth or the height, what? I get 8/3. Okay? So your z is 8/3. So it's going to be a 4/3 by 2 by 8/3 box. And then the actual max volume is, you just multiply all these together. What is 4/3 times 2 times 8/3? And that's your max volume. You multiply all that together, and you should get 64/9 cubic units. And there's your max volume. And there's your final answer to that problem. Questions?
Okay.
Okay, hold on a quick second. So this is a copy of your quiz. You can't see it, but this is my solution key for it. So I want to just quickly go over just briefly how you tackle example 11, because there's going to be a problem similar to that on your exam. So let me just hand wave through this. They're asking for there's your profit function for producing X units of product A and Y units of product B. How do you maximize this profit? Okay, so well, you're just going to, you know, do all the usual. You're going to get PX, you're going to get PY, set them equal to 0, and it turns out you're only going to get 1 critical point, which is nice. And then you're going to get D, which is going to be PXX times PYY minus PXY squared, to prove to me that you really are maximizing the profit. And then you'll give the actual profit. So for those of you that want to try your hand at this one, and I encourage you to do so, and I do have office hours today at noon, so I encourage you to come in if you want to talk more about anything. It turns out the critical point is where you have a production level of 2,000 products of A, whatever that product is, and then 4,000 units of product B. And the actual max profit is where you evaluate your profit function at this critical point. And I think your profit is in dollars. So you're going to get, I think your profit is going to be $18,000. Not bad, okay? So this is just like one of those business calculus type problems. But the business calculus problem I put on the quiz is a little bit trickier, because I'm going to give you a revenue function that's going to look like R of X. Revenue is the total amount of money that comes into your shop. And then I give you a costs function, C of X, and then I ask you to maximize the profit without giving you the profit function. So you need one extra fact, because you maybe didn't take an economics class. The profit, that's the money that your shop gets to keep, is equal to the total amount of money that comes into your shop minus your costs. You know, you have to pay off, you know, your employees and pay the rent for your shop and pay the gas and electric bill and all that stuff. And so after you pay off all the folks, whatever money's left is your profit. Okay, so you'll have to put together your profit function and then do the calculus. Okay, and I'm done. Happy Friday. Goodbye. You want to stay for 5 minutes? I can do that. And I'll stop the recording.